हेलो एवरीवन, वंस अगेन वेलकम बैक टू आवर चैनल बीट द नीट। और आज हम करने जा रहे हैं क्लास 11th यूनिट 6 थर्मोडायनेमिक्स। ये आपकी रिक्वेस्ट के अकॉर्डिंग ही मैं ऑडियो बुक रिकॉर्ड कर रही हूँ बच्चों। दिस इज ओनली एन ऑडियो बुक, सो बच्चों वेन एवर यू आर लिसनिंग इट बी स्पेसिफिक विद दैट, इट्स नॉट द एक्सप्लेनेटरी वन। बच्चों इसको अपने दोस्तों के साथ में ज़्यादा से ज़्यादा शेयर करिए ताकि उनको भी इसका बेनिफिट मिल सके। और साथ ही साथ कमेंट सेक्शन में आप मुझे ये भी बताते जाइएगा कि और क्या इंप्रूवमेंट चाहिए, और आफ्टर केमिस्ट्री आप किसकी ऑडियो बुक चाहते हैं। अगर आपको बायो में ही किसी और बुक की ऑडियो बुक चाहिए या केमिस्ट्री में, तो आप वो नेम्स मुझे सजेस्ट करिए, सो देन आई विल चूज दैट विच ऑडियो बुक आई हैव टू प्रिपेयर फर्स्ट। सो चलिए टाइम वेस्ट नहीं करते हैं, शुरू करते हैं। यूनिट 6 थर्मोडायनेमिक्स। It is the only physical theory of universal content concerning which I am convinced that, within the framework of the applicability of its basic concept, it will never be overthrown. Albert Einstein. Chemical energy stored by molecules can be released as heat during chemical reaction when a fuel like methane, cooking gas, or coal burns in air. The chemical energy may also be used to do mechanical work when a fuel burns in an engine, or to provide electrical energy through a galvanic cell like dry cell. Thus, various forms of energy are interrelated, and under certain conditions, these may be transformed from one form into another. The study of these energy transformation forms the subject matter of thermodynamics. The laws of thermodynamics deal with the energy changes of macroscopic system involving a large number of molecules rather than microscopic systems containing a few molecules. Thermodynamics is not concerned about how and at what rate these energy transformations are carried out, but is based on initial and final states of system undergoing the change. Laws of thermodynamics apply only when a system is in equilibrium or moves from one equilibrium state to another equilibrium state. Macroscopic properties like pressure and temperature do not change with time for a system in equilibrium state. In this unit, we would like to answer some of important questions through thermodynamics, like how do we determine the energy changes involved in a chemical reaction or process? Will it occur or not? What drives a chemical reaction or process? To what extent do the chemical reactions proceed? 6.1 Thermodynamic terms. We are interested in chemical reactions and the energy changes accompanying them. For this, we need to know certain thermodynamic terms. These are discussed below. 6.1.1 The system and the surroundings. A system in thermodynamics refers to that part of universe in which observations are made, and remaining universe constitutes the surroundings. The surroundings include everything other than the system. System and the surroundings together constitute the universe. The universe is equals to the system plus the surroundings. However, the entire universe other than the system is not affected by the changes taking place in the system. Therefore, for all practical purposes, the surroundings are the portion of the remaining universe which can interact with the system. Usually, the region of space in the neighborhood of the system constitutes its surroundings. For example, if we are studying the reaction between two substances A and B kept in a beaker, the beaker containing the reaction mixture is the system, and the room where the beaker is kept is the surroundings. Here you can see the figure 6.1 system and the surroundings. Note that the system may be defined as the physical boundaries like beaker or test tube, or the system may simply be defined by a set of Cartesian coordinate specifying a particular volume in space. It is necessary to think of the system as separated from the surroundings by some sort of wall, which may be real or imaginary. The wall that separates the system from the surroundings is called boundary. This is designed to allow us to control and keep track of all movements of matter and energy in or out of the system. 6.1.2 Types of system. We further classify the systems according to the movements of matter and energy in or out of the system. Number 1, open system. In an open system, there is exchange of energy and matter between system and surroundings. Figure 6.2a. The presence of reactants in an open beaker is an example of an open system. Here the boundary is an imaginary surface enclosing the beaker and reactants. Number 2, closed system. In a closed system, there is no exchange of matter but exchange of energy is possible between system and the surroundings. Figure 6.2b. The presence of reactants in a closed vessel made of conducting material, example copper or steel, is an example of a closed system. Here you can see the board diagram of open system, closed system, and the C1 is isolated system. Number 3, isolated system. In an isolated system, there is no exchange of energy or matter between the system and the surroundings. The presence of reactants in a thermos flask or any other closed insulated vessel is an example of an isolated system. 6.1.3, the state of the system. The system must be described in order to make any useful calculation by specifying quantitatively each of the properties such as its pressure, volume, and temperature, as well as the composition of the system. We need to describe the system by specifying it before and after the change. You would recall from your physics course that the state of a system in mechanics is completely specified at a given instant of time by the position and velocity of each mass point of the system. In thermodynamics, a different and much simpler concept of state of a system is introduced. It does not need detailed knowledge of motion of each particle because we deal with average measurable properties of the system. We specify the state of the system by state functions or state variables. The state of a thermodynamic system is described by its measurable or macroscopic properties. We can describe the state of a gas by quoting its pressure, volume, temperature, amount, etc. Variables like P, V, T are called state variables or state functions because their values depends only on the state of the system and not on how it is reached. In order to completely define the state of a system, it is not necessary to define all the properties of the system, as only a certain number of properties can be varied independently. This number depends on the nature of the system. Once these minimum number of macroscopic properties are fixed, others automatically have definite values. The state of the surrounding can never be completely specified. Fortunately, it is not necessary to do so. 6.1.4, the internal energy as a state function. When we talk about our chemical system losing or gaining energy, we need to introduce a quantity which represents the total energy of the system. It may be chemical, electrical, mechanical, or any other type of energy you may think of. The sum of all these is the energy of the system. In thermodynamics, we call it the internal energy, U, of the system, which may change when heat passes into or out of the system, work is done on or by the system, matter enters or leaves the system. These systems are classified accordingly as you have already studied in section 6.1.2. A. Work. Let us first examine a change in internal energy by doing work. We take a system containing some quantity of water in a thermos flask or in an insulated beaker. This would not allow exchange of heat between the system and surroundings through its boundary, and we call this type of system as adiabatic. The manner in which the state of such a system may be changed will be called adiabatic process. Adiabatic process is a process in which there is no transfer of heat between the system and the surroundings. Here, the wall separating the system and the surroundings is called the adiabatic wall, figure 6.3. Let us bring the change in the internal energy of the system by doing some work on it. Let us call the initial state of the system as a state A and its temperature as TA. Let the internal energy of the system in state A be called UA. We can change the state of the system in two different ways. One way, we do some mechanical work, say 1 kilojoule, by rotating a set of small pedals and thereby churning water. Let the new state be called B state and its temperature as TB. It is found that TB is greater than TA and the change in temperature delta T is equals to TB minus TA. Let the internal energy of the system in state B be UB and the change in internal energy delta U is equals to UB minus UA. Second way, We now do an equal amount of electrical work with the help of an immersion rod and note down the temperature change. We find the change in temperature is same as the earlier case, say TB minus TA. In fact, the experiments in the above manner were done by J.P. Joule between 1840 to 50, and he was able to show that a given amount of work done on the system, no matter how it was done, irrespective of path, produced the same change of state as measured by the change in the temperature of the system. So it seems appropriate to define a quantity, the internal energy U, whose value is characteristic of the state of a system, whereby the adiabatic work WAD required to bring about a change of state is equal to the difference between the value of U in one state and that in another state, delta U. That is, delta U is equals to U2 minus U1 is equals to WAD. Therefore, internal energy U of the system is a state function. By conventions of IUPAC in chemical thermodynamics, the positive sign expresses that WAD is positive when work is done on the system and the internal energy of system increases. Similarly, if the work is done by the system, WAD will be negative because internal energy of the system decreases. Can you name some other familiar state functions? Some of other familiar state functions are V, P, and T. For example, if we bring a change in temperature of the system from 25 to 35 degrees Celsius, the change in temperature is equals to plus 10 degrees Celsius. Whether we go straight up to 35 or we cool the system for a few degrees, then take the system to the final temperature. Thus, T is a state function and the change in temperature is independent the route taken. Volume of water in a pond, for example, is a state function because change in volume of its water is independent of the route by which water is filled in the pond, either by rain or by tubewell or by both. B. Heat. We can also change the internal energy of a system by transfer of heat from the surroundings to the system or vice versa, without expenditure of work. This exchange of energy, which is a result of temperature difference, is called heat. Q. Let us consider bringing about the same change in temperature, that is the same initial and final state as before in section 6.1.4a by transfer of heat through thermally conducting walls instead of adiabatic walls. Figure 6.4, a system which allows heat transfer through its boundary. We take water at temperature TA in a container having thermally conducting walls, say made of copper, and enclose it in a huge heat reservoir at temperature TB. The heat absorbed by the system, that is water, Q, can be measured in the term of temperature difference, TB minus TA. In this case, change in internal energy delta U is equals to Q when no work is done at constant volume. By conventions of IUPAC in chemical thermodynamics, the Q is a positive when heat is transferred from the surroundings to the system and the internal energy of the system increases, and Q is negative when heat is transferred from system to the surroundings, resulting in decrease of the internal energy of the system. Earlier, negative sign was assigned when the work is done on the system and positive sign when the work is done by the system. This is still followed in physics books, although IUPAC has recommended the use of new sign convention. See the general case. Let us consider the general case in which a change of state is brought about both by doing work and by transfer of heat. We write change in internal energy for this case as delta U is equals to Q plus W. For a given change in state, Q and W can vary depending on how the change is carried out. However, Q plus W is equals to delta U will depend only on initial and final state. It will be independent of the way the change is carried out. If there is no transfer of energy as heat or as work isolated system, that is, if W is equals to 0 and Q is equals to 0, then delta U is equals to 0. The equation 6.1, that is delta U is equals to Q plus W, is mathematical statement of the first law of thermodynamics, which states that the energy of an isolated system is constant. It is commonly stated as the law of conservation of energy, that is, energy can neither be created nor be destroyed. Note, there is considerable difference between the character of the thermodynamic property energy and that of mechanical property such as volume. We can specify an unambiguous, that is absolute, value for volume of a system in a particular state, but not the absolute value of the internal energy. However, we can measure only the changes in the internal energy, delta U of the system. Application 6.2. Many chemical reactions involve the generation of gases capable of doing mechanical work or the generation of heat. It is important for us to quantify these changes and relate them to the changes in the internal energy. Let us see how. 6.2.1 Work. First of all, let us concentrate on the nature of work a system can do. We will consider only mechanical work, that is pressure volume work. For understanding pressure volume work, let us consider a cylinder which contains 1 mole of an ideal gas fitted with a frictionless piston. Total volume of the gas is Vi and pressure of the gas inside is P. If external pressure is Px, where is greater than P, piston is moved inward till the pressure inside becomes equal to Pex. Let this change. See the figure 6.5a. Work done on an ideal gas in a constant external pressure Pex, that is in single step, is equal to the shaded area. Let this change be achieved in a single step and the final volume be Vf. During this compression, suppose piston moves a distance L and its cross-sectional area of the piston is A. The volume change is equals to L into A is equals to delta V is equals to Vf minus Vi. We also know pressure is equals to force upon area. Therefore, force on the piston is equals to P dot A. If W is the work done on the system by movement of the piston, then W is equals to force into distance is equals to Pex dot A dot L. Pex dot minus delta V is equals to minus Pex delta V is equals to minus Pex in bracket Vf minus Vi. The negative sign of this expression is required to obtain conventional sign for W, which will be positive. It indicates that in case of compression work is done on the system, here Vf minus Vi will be negative and negative multiplied by negative will be positive. Hence, the sign obtained for the work will be positive. If the pressure is not constant at every stage of compression but changes in number of finite steps, work done on the gas will be summed over all the steps and will be equal to negative summation PWV. Here you can see the 6.5b plot. If the pressure is not constant but changes during the process such that it is always infinitesimally greater than the pressure of the gas, then at each stage of compression the volume decreases by an infinitesimal amount dV. In such a case, we can calculate the work done on the gas by the relation. Here you can see this relation. Here Px at each stage is equal to Pin, that is initial, plus dP in case of compression. Figure 6.5c. In an expansion process under similar conditions, the external pressure is always less than the pressure of the system. That is Pex is equals to P initial minus dP. In general case, we can write Pex is equals to P initial plus minus dP. Such processes are called reversible processes. A process or change is said to be reversible if a change is brought out in such a way that the process could at any moment be reversed by an infinitesimal change. A reversible process proceeds infinitely slowly by a series of equilibrium states such that system and the surroundings are always in near equilibrium with each other. Processes other than reversible processes are known as irreversible processes. Here you can see the figure 6.5c. In chemistry, we face problems that can be solved if we relate the work term the internal pressure of the system. We can relate work to internal pressure of the system under reversible condition by writing equation. Here you can see the equation. Now the pressure of the gas P, which we can write as P now, can be expressed in terms of its volume through gas equation. For n mole of an ideal gas, that is PV is equals to nRT. P is equals to nRT upon V. Therefore, at constant temperature, here you can see the reaction. The final reaction is minus 2.303 is nRT log Vf upon Vi. Free expansion. Expansion of a gas in a vacuum, Pax is equals to 0, is called free expansion. No work is done during free expansion of an ideal gas, whether the process is reversible or irreversible. Now we can write equation 6.1 in number of ways depending on the type of processes. Let us substitute W is equals to minus PEX delta V in equation 6.1 and we get delta U is equals to Q minus PEX delta V. If a process is carried out at constant volume, it means the delta V is equals to 0, then delta U is equals to QV. The subscript V in QV denotes that heat is supplied at constant volume. Isothermal and free expansion of an ideal gas. For isothermal, T constant expansion of an ideal gas into vacuum, W is equals to 0. Since PEX is equals to 0, also Joule determined experimentally that Q is equals to 0, therefore delta U is equals to 0. Here you can see the equation 6.1 and the complete calculation. First, for isothermal irreversible change, Q is equals to minus W is equals to PEX VF minus VI. And in the second, for isothermal reversible change, the final equation is 2.303 nRT log VF upon VI. And third, for the adiabatic change, Q is equals to 0, delta U is equals to W adiabatic. 6.2.2, that is enthalpy H, a useful new state function. We know that heat absorbed at constant volume is equal to change in the internal energy, that is delta U is equals to QV. But most of chemical reactions are carried out not at constant volume but in flask or test tubes under constant atmospheric pressure. We need to define another state function which may be suitable under these conditions. We may write equation 6.1 as delta U is equals to QP minus P delta V at constant pressure, where QP is heat absorbed by the system and minus P delta V represents expansion work done by the system. Let us represent the initial state by subscript 1 and final state by 2. We can rewrite the above equation as U2 minus U1 is equals to QP minus P V2 minus V1. On rearranging, we get QP is equals to U2 plus PV2 minus U1 plus PV1. Now we can define another thermodynamic function, the enthalpy H. H is equals to U plus PV. So equation 6.6 becomes QP is equals to H2 minus H1 is equals to delta H. Although Q is a path dependent function, H is a state function because it depends on U, P and V, all of which are a state function. Therefore, delta H is independent of path, hence QP is also independent of path. For finite changes at constant pressure, we can write equation 6.7 as delta H is equals to delta U plus delta PV. Since P is constant, we can write delta H is equals to delta U plus P delta V. It is important to note that when heat is absorbed by the system at constant pressure, we are accurately measuring changes in the enthalpy. Remember, delta H is equals to QP, heat absorbed by the system at constant pressure. Delta H is negative for exothermic reactions which evolve heat during the reaction, and delta H is positive for endothermic reactions which absorb heat from the surroundings. At constant volume, delta V is equals to 0, delta U is equals to QV, therefore equation 6.8 becomes delta H is equals to delta U is equals to QV. The difference between delta H and delta U is not usually significant for systems consisting of only solids and or liquids. Solids and liquids do not suffer any significant volume changes upon heating. The difference, however, becomes significant when gases are involved. Let us consider a reaction involving gases. If Va is the total volume of the gaseous reactants, Vb is the total volume of the gaseous product. Na is the number of moles of gaseous reactants and Nb is the number of moles of gaseous products. All at constant pressure and temperature. Then using the ideal gas law, we write PVA is equals to NART, PVB is equals to NBRT, PVB minus PVA is equals to NBRT minus NART is equals to NB minus NART. Then P common lene par VB minus VA is equals to NB minus NA and bracket close then RT. So it means the P delta V is equals to delta N RT. Here delta N refers to the number of moles of gaseous products minus the number of moles of gaseous reactants. Substituting the value of P delta V from equation 6.9 in equation 6.8, we get delta H is equals to delta U plus delta N GRT. The equation 6.10 is useful for calculating delta H and delta U and vice versa. B. Extensive and intensive properties. In thermodynamics, a distinction is made between extensive property and intensive properties. An extensive property is a property whose value depends on the quantity or size of matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity, etc. are extensive properties. Those properties which do not depend on the quantity or size of matter present are known as intensive property. For example, temperature, density, pressure, etc. are intensive property. A molar property xm is the value of an extensive property x of the system for 1 mole of the substance. If n is the amount of matter, then xm is equals to x upon n is independent of the amount of matter. Other examples are molar volume, that is Vm, and molar heat capacity, Cm. Let us understand the distinction between extensive and intensive properties by considering a gas enclosed in a container of volume V and at temperature T. Let us make a partition such that volume is halved. Each part now has 1/2 of the original volume, V upon 2, but the temperature will still remain the same, that is the T. It is clear that volume is an extensive property and the temperature is an intensive property. C. Heat capacity. Here you can see the figure 6.6a and 6.6b. C. Heat capacity. In this subsection, let us see how to measure heat transfer to a system. This heat appears as a rise in temperature of the system in case of heat absorbed by the system. The increase of temperature is proportional to the heat transfer. Q is equals to coefficient into delta T. The magnitude of the coefficient depends on the size, composition, and nature of the system. We can also write it as Q is equals to C delta T. The coefficient C is called the heat capacity. Thus, we can measure the heat supplied by monitoring the temperature rise provided we know the heat capacity. Where C is large, a given amount of heat results in only a small temperature rise. Water has large heat capacity, that is, a lot of energy is needed to raise its temperature. C is directly proportional to amount of substances. The molar heat capacity of a substance Cm is equals to C upon N is the heat capacity for 1 mole of the substance and is the quantity of heat needed to raise the temperature of 1 mole by 1 degree Celsius or 1 Kelvin. Specific heat, also called specific heat capacity, is the quantity of heat required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. For finding out the heat Q required to raise the temperatures of a sample, we multiply the specific heat of the substance C by the mass m and temperature change delta T, as Q is equals to C into m into delta T is equals to C delta T. D. The relationship between Cp and Cv for an ideal gas. At constant volume, the heat capacity C is denoted by Cv, and at constant pressure, this is denoted by Cp. Let us find the relationship between the two. We can write the equation for heat Q. At constant volume, as Qv is equals to Cv delta T is equals to delta U. At constant pressure, Qp is equals to Cp delta T is equals to delta H. The difference between Cp and Cv can be derived for an ideal gas as here the final delta H is equals to delta U plus R delta T. So delta H is equals to delta U plus R delta T. On putting the values of delta H and delta U, we have final reaction, that is Cp minus Cv is equals to R. 6.3 Measurement of delta U and delta H calorimetry. We can measure energy changes associated with chemical or physical processes by an experimental technique called calorimetry. In calorimetry, the process is carried out in a vessel called calorimeter, which is immersed in a known volume of a liquid. Knowing the heat capacity of the liquid in which calorimeter is immersed and the heat capacity of the calorimeter, it is possible to determine the heat evolved in the process of measuring temperature changes. Measurements are made under two different conditions. Number 1, at constant volume, Qv, at constant pressure, Qp. A. Delta U measurements. For a chemical reaction, heat absorbed at constant volume is measured in a bomb calorimeter. Here a steel vessel is immersed in a water bath. The whole device is called calorimeter. The steel vessel is immersed in water bath to ensure that no heat is lost due to the surroundings. A combustible substance is burned in pure dioxygen supplied in the steel bomb. Heat evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. Since the bomb calorimeter is sealed, its volume does not change, that is, the energy changes associated with reactions are measured at constant volume. Under these conditions, no work is done as the reaction is carried out at constant volume in the bomb calorimeter. Even for reactions involving gases, there is no work done as delta V is equals to 0. Temperature change of the calorimeter produced by the completed reaction is then converted to QV by using the known heat capacity of the calorimeter with the help of equation 6.1.11. Delta H, measurement of heat change at measurement of heat change at constant pressure, generally under atmospheric pressure, can be done in a calorimeter shown in figure 6.8. Here is the figure 6.8. We know that delta H is equals to QP at constant P, and therefore heat absorbed or evolved QP at constant pressure is also called the heat of reaction or enthalpy of reaction delta RH. In an exothermic reaction, heat is evolved and system loses heat to the surroundings. Therefore, QP will be negative and delta RH will also be negative. Similarly, in an endothermic reaction, heat is absorbed, QP is positive and delta RH will be positive. 6.4 Enthalpy change, delta RH of a reaction enthalpy. In a chemical reaction, reactants are converted into products and is represented by reactant gives out products. The enthalpy change accompanying a reaction is called the reaction enthalpy. The enthalpy change of a chemical reaction is given by the symbol delta RH. Delta RH is equals to sum of enthalpies of product minus sum of enthalpies of reactants. Here you can see. Here the symbol sigma is used for summation and AI and BI are the stoichiometric coefficients of the products and reactants respectively in the balanced chemical equation. For example, for the reaction CH4 plus 2O2 gives out CO2 plus 2H2O. Here you can see the complete delta HM value, and delta HM is the molar enthalpy here, and the complete delta RH value you can see here. Enthalpy change is a very useful quantity. Knowledge of this quantity is required when one need to plan the heating or cooling required to maintain an industrial chemical reaction at constant temperature. It is also required to calculate temperature dependence of equilibrium constant. A. Standard enthalpy of reactions. Enthalpy of reaction depends on the conditions under which a reaction is carried out. It is therefore necessary that we must specify some standard conditions. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in their standard states. The standard state of a substance at a specified temperature is its pure form at 1 bar. For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. The standard state of solid iron at 500 K is pure iron at 1 bar. Usually data are taken at 298 Kelvin. Standard conditions are denoted by adding the superscript negative to the symbol delta H. Example, delta H negative. The B, enthalpy changes during phase transformation. Phase transformations also involve energy changes. Ice, for example, requires heat for melting. Normally, this melting takes place at constant pressure, that is atmospheric pressure, and during phase change, temperature remains constant at 273 Kelvin. H2O gives out H2O liquid. Initially, it was solid, so delta H of fusion is equals to 6 kilojoule per mole. Here, delta H fusion is enthalpy of fusion in standard state. If water freezes, then process is reversed and equal amount of heat is given off to the surrounding. The enthalpy change that accompanies melting of 1 mole of solid substance in a standard state is called standard enthalpy of fusion or molar enthalpy of fusion. Melting of a solid in is endothermic, so all enthalpies of fusion are positive. Water requires heat for evaporation at constant temperature of its boiling point Tb, and at constant pressure H2O gives out H2O gaseous, so delta vaporization H is equals to plus 40.79 kilojoule per mole is the standard enthalpy of vaporization. Here you can see the table, that is the standard enthalpy changes of fusion and vaporization. Here TF and TB are melting and boiling points respectively. Amount of heat required to vaporize 1 mole of liquid at constant temperature and standard pressure. 1 bar is called its standard enthalpy of vaporization or molar enthalpy of vaporization. Sublimation is direct conversion of a solid into its vapor. Solid CO2 or dry ice sublimes at 195 Kelvin with delta sublime H is equals to 25.2 kilojoule per mole. Naphthalene sublimes slowly, and for this delta H sublimation is equals to 73.0 kilojoule per mole. Standard enthalpy of sublimation, delta H sublimation, is the change in enthalpy when 1 mole of solid substance sublimes at constant temperature and under standard pressure. The magnitude of the enthalpy change depends on the strength of the intermolecular interaction in the substance undergoing the phase transformations. For example, the strong hydrogen bonds between water molecules hold them tightly in liquid phase. For an organic liquid such as acetone, the intermolecular dipole-dipole interactions are significantly weaker. Thus, it requires less heat to vaporize 1 mole of acetone than it does to vaporize 1 mole of water. Table 6.1 give values of standard enthalpy change of fusion and vaporization for some substances. This is the table 6.2, that is the standard molar enthalpies of formation at 298 Kelvin of a few selected substances. Rest of the chapter I will record in the next part. So just revise the chapter with this part 1, and in the evening I will upload the second part of this thermodynamics chapter. So share it with your friends so that they will also get the benefit of it, and don't forget to comment, like, right? So take care everyone. Bye bye. See you soon in the next video. Till then, just stay tuned with me. Bye bye. Take care.